We continue in this lecture with our discussion of Einstein's special theory of relativity. We'll begin with a discussion of event durations. Examples of events: the melting of a cube of ice, the burning of a candle, the life and death of a fundamental particle such as a muon, the time it takes to climb a mountain. Any event whatsoever is subject to the laws discovered by Albert Einstein. I indicate here an event of some sort. As I said, the burning out of a candle flame, the melting of an ice cube, the falling of an object. I show an observer's eye. This observer is not moving with respect to this event. Maybe the observer is moving, but in her hand is an ice cube that is melting. And so she measures the amount of time it takes that ice cube to melt. She's not moving relative to that ongoing event. Another example of a measurement of a time interval as seen by a person not moving with respect to the event itself. Consider a runner on a racetrack. The event is the running. The running is taking place wherever the runner is. So the runner would measure a certain time for that event, being at rest with respect to that event. Now contrast that situation with the person at a track meet in the stands, watching the runner travel the distance. The runner, as we've just established, is at rest with respect to that event. Well, so what? Well, we'll get to that. The person in the stand, however, is moving relative to that event. Now, that person in the stand is not moving relative to the stands, not moving relative to the ground, but because the runner is in motion, the observer in the stand is moving relative to the runner. Now, that person will measure a different time for the event, which is the amount of time it takes the runner to complete that journey. So let's return to the whiteboard. We're going to indicate that the observer who is at rest relative to the event has a relative speed v equal to 0. She measures what we call the proper time. We subscript that proper time t symbol with a 0 to indicate that this observer is at rest, has a speed 0 relative to the event. A second observer shown here is looking at the same event, but that observer's relative velocity is not 0. This person is moving relative to the event. An example of that would be back to that track meet. There is a runner and a second runner. The second runner is looking at the first runner. Each object or observer, each person, each runner is moving relative to the other. Their relative speed is not 0. The amount of time those runners say the event took, the completion of the run, is a number different from what was observed before by the person who is stationary with respect to the event. We don't subscript that event duration. We note that the speed, relative speed, is not 0. Now, the two different situations, the two different times that are measured are related to each other. We first described what was called the proper time, and now we've just described the time observed by a person who's moving relative to that place where the event is occurring. In the case of an ice cube that is melting in a person's hand, the person holding the ice cube is always at rest relative to where this event is taking place, her hand. An observer walking away from that melting ice cube likewise might be moving with zero velocity relative to the ice cube if they're both moving in the same direction at the same speed. So each says the other is not moving relative to it. The time that's calculated by those who are moving relative to an event, symbolized T, no subscript, is equal to this equation. You'll recognize beta from our previous study. It's the ratio of the relative speed v to the speed of light. This time is called the dilated time because it's a longer time than the so-called proper time. You can see that t is longer than t naught because the denominator is a number at best equal to 1 and for sure otherwise less than 1, because beta is a fraction less than 1. It's the ratio of v to c. Its square is still a fraction less than 1, so the parentheses is less than 1, and the square root of the parentheses is less than 1 is still less than 1, and so we're dividing the numerator by a number less than 1, so t is equal to a number larger than t naught. So I'll record that fact here. T is at best equal to t naught, otherwise greater than t naught. Let's work a simple example of what we call time dilation. The word to dilate, you may know, means to widen or to increase or to enlarge. And that is what's happening in the case of observers moving relative to the event. Suppose beta is 0.90 and a particular proper time that's measured is 16 minutes. The observer who has a relative speed of 0.9 times c, in other words, a beta of 0.90, observes that the time it took for the event to be completed, and we won't specify what the event is 36.7 meters using the time dilation equation. Now it's important to understand that the observer that says the amount of time the event took to be completed, that observer is not measuring a false time or somehow suffering from or experiencing an illusion. It's the actual time for this observer. It's the real time. For this person, his or her reality is that the time it took for the event to occur, that many minutes, more than twice what the other observer said. Both observers are correct in their frame of reference, in their world, in their reality. Very surprising result. Totally unfathomable. Don't try to understand it. Just know what it means to speak of a proper time and a dilated time. Both numbers are as correct as the other. Well, you should be at this point quite perplexed, find it very hard to understand. If you think you understand it after much thought, think again, because you don't understand it. Just accept it. Relax. That's it for today. Stay safe. Don't touch your face.